We have seen in the previous video how to calculate the chi-square between two qualitative variables. This video will give you a step-by-step procedure to verify if the two variables are independent one from the other. Remember that the chi-square we calculate tells us how far away our observed values are from values we would expect under pure probability. The main idea behind the chi-square test for independence is that the closer we are to pure probability, the lower the chance that the two variables are related to each other. Or, in other words, if our chi-square is very low or close to zero, we can say that our variables do not have a relationship one with the other, or that they are independent one from the other. Just like we did with the z and the t-test from the mean, we must ask ourselves, is the chi-square I've just calculated far enough from pure probability to say that there is a relationship between the two qualitative variables? To answer this question, we will again go through the 7 steps of hypothesis testing. So let's do this with an example. Imagine that you wish to determine whether there is a relationship between the gender and the alcohol consumption of individuals. Your data comes in this format in a table of contingency. We have two qualitative variables, alcohol consumption with the values low, moderate, and high, and gender with the values male and female. So each table of contingency has a given degree of freedom, which is calculated by multiplying the number of rows minus 1 times the number of columns minus 1. It's important to note that the number of rows and columns refer to columns and rows that hold original values, not the totals or the headings. As such, the degree of freedom for this table is 2 rows minus 1 times 3 columns minus 1 for a degree of freedom of 2. Step 1 is to choose the appropriate test. The conditions here are that you have two qualitative variables, which is what we have with gender and alcohol consumption, and some key words would be looking for a relationship between these two variables, testing the independence of these two variables, or verifying if one variable influences the other. When you have these conditions, then you choose to do a chi-square test. Our second step is to state the statistical hypotheses. Now, the way we're going to state these depends on which variable influences the other. So we will have an independent variable and a dependent variable. Here are a few examples. The age of an individual influences the height of that individual. So the height depends on the age. The soil type in your garden will influence the types of veggies that you can grow there. So the types of veggies depends on the soil type. The amount of sunscreen you put on influences the intensity of a sunburn. So the intensity of a sunburn depends on the amount of sunscreen. Your annual salary influences the rent value of a house that you can afford. The speed at which you walk influences the time taken to get to school. And a last example, air temperature influences the type of precipitation, snow or rain, so the type of precipitation depends on the temperature. Let's go back to our example. Again, you must state both the null and the alternative hypothesis. But before you state your hypotheses, you must first determine which variable is the independent one and which is the dependent variable. So here we have gender and alcohol consumption. I think we can safely say that the consumption of alcohol does not influence an individual's gender. So alcohol consumption depends on the gender. So gender is the independent variable and alcohol consumption is the dependent variable. Now we can state our hypotheses. The null hypothesis states that there is no relationship between the two variables, so you can state it like so. A person's alcohol consumption is independent of their gender. The alternative hypothesis states the absolute opposite, so you can state it like so. A person's alcohol consumption depends on their gender. Step 3 is the level of significance. Just like previously, unless otherwise specified, the level of significance is 0.05. So because there's no other indication, we will use for this example a level of significance of 0.05. Step 4, again, is to determine the critical value. Before we go further, I need to introduce the chi-square distribution. Just like the sampling distribution of the mean always takes on the shape of a normal distribution, the sampling distribution of chi-square always takes on the same basic shape, which is this. Just like the t-curve, the chi-square curve can be more or less pronounced depending on the degree of freedom, but the general shape stays the same. Notice how the curve starts at 0, which is true no matter the degree of freedom. This makes sense when you think of what the chi-square represents. It indicates how far apart or how close your observed values are from what we would be expected under pure probability. And the nearest distance, or the closest you can be, is 0. Just like in the other hypothesis testing we did before, our critical value determines the objective limit where too far from 0 is just too far. Let's imagine that our calculated chi-square value would be here. Of course it's not 0, but it's definitely not very far from 0, right? But what if our calculated value falls here? Then it's not quite as clear as the first one, isn't it? That's where the level of significance comes in. We have determined our level of significance to be 5%, and chi-square tests have the fantastic characteristic of always being one-tailed, so this 5% area will always be to the right, like so. Now, we can see that the second calculated value is clearly in the rejection zone. But how do we determine this critical value? We must refer to the chi-square table. The chi-square table is a bit different than the other tables we have seen, so let's take a few moments to go through it. Just like the t-table, the values in the red rectangle here indicate the critical chi-square values. Each one of these values refer to a specific area to the right of the critical value and to a specific degree of freedom. If you remember our example, our table had a degree of freedom of 2, and our level of significance, or area to the right of the critical value, is of 0.05, leading us to a critical chi-square value of 5.991. The fifth step is to calculate our chi-square for our results. First, we must find the expected values. Remember, we must do this for every cell in our contingency table. To obtain an expected value, we take the total of the cell's column, multiply it by the total of the cell's row, and divide the result by the grand total of the table. So for the first cell, we have an expected value of 9.13. Here are all of the expected values for this given contingency table. Now we can compute the chi-square value for our distribution. Now for this, for each cell in our table, we will take the observed value minus the expected value, all of that squared, divided by the expected value. So for this cell, these are the values you'd plug into the equation, which would give you a chi-square of 0.08. You must do this for every cell and then sum up each one of your chi-square values. You can check it out on your own, or you can trust me when I say that the total chi-square for a distribution is 0.283. Step 6 is to take the statistical decision. Recall that the critical chi-square value was of 5.991. Our calculated value was of 0.283, so falls approximately here. As you can see, we are very far from the area of rejection. As such, we do not reject the null hypothesis. Step 7 is to resume the results, so you can state that there is not enough evidence to claim that an individual's gender influences their alcohol consumption. Now it's your turn. Return to the example you did in the last video and indicate if the following statement you see on the screen is true or false. An individual snacking preference actually depends on their gender.